Education is what's important. Training, preparation for the expected. Education, preparation for the unexpected.
To all who shall see these presents, greetings. On behalf of Marine Corps University, the Marine Corps University Foundation, and the Krulak Center for Innovation and Future Warfare, welcome back to the BrewCast, our series designed to connect the worlds of the warfighter and PME with the best in innovative and creative thought. I'm your host, Major Nate Janikin, Operations Officer at the Krulak Center. Before we begin, please remember that all opinions expressed here are those of the individual and do not necessarily reflect the views of the Krulak Center, Marine Corps University, United States Marine Corps, or any other agency of the U.S. government. By the time Skynet became self-aware, it had spread into millions of computer servers across the planet, ordinary computers in office buildings, dorm rooms, everywhere. It was software in cyberspace. There was no system core. It could not be shut down. The attack began at 6:18 p.m., just as he said it would, Judgment Day. Some listeners may recognize this as the ending to Terminator 3, and in Terminator canon, Judgment Day was August 29th, 1997. Thankfully, we've gone past that date with no self-produced robot apocalypse. And while AI sounded far-fetched enough to be in Hollywood science fiction, today it's a hot topic and touching more and more areas of our everyday lives. Today, our guest is Dr. Jack Long. Dr. Long is a Marine reservist at the Office of Naval Research, where as an IMADEP, he served as the deputy to the Navy Chief AI Officer, Brett Vaughn, since 2020. He was activated to full-time service in June 2023 to backfill upon Mr. Vaughn's retirement at the end of June. He holds a PhD from Johns Hopkins University, having done his undergraduate and doctorate work there. Upon finishing his PhD work in 2005, he joined the Marines and was commissioned as second lieutenant in the Marine Corps. He spent 8 years on active duty, deploying 6 times to Central Command in support of OIF, OEF, and other operations. After leaving active duty, he attended the University of Oxford, where he earned an MBA, graduating with distinction. He stayed on at the university in an innovation fellowship, working to build startups based on university IP, and was the CEO designate of an early stage spinout. He returned to the States and joined McKinsey & Company, working out of the DC office, where he worked on numerous strategy and transformation projects with clients in the public, private, and government sector. He was recruited to lead the post-merger integration efforts in the North American business unit of MIA, the world's leader in augmented identity. He stayed on as a leader in the strategy, innovation, and corporate development functions before leaving to join a boutique startup A&D consulting firm, helping to grow it to an elite firm that partners with clients to help them solve some of their thorniest strategy, operations, and transformation challenges. Sir, welcome to the BrewCast.
Thank you.
And I'll turn the floor over to you.
Appreciate that. And you mentioned Skynet, you mentioned Hollywood, and I would say the single biggest thing about AI that I think we have a problem with is the fact that most people's understanding of AI, what artificial intelligence is, has come from Hollywood. And Hollywood writers don't know what artificial intelligence is very much either, but it's a great story, something to use to drive a story with. We've got this big magical machine that's evil, or it's good, or it's something. So what people think of as artificial intelligence has come from the movies, and we know that when you allow Hollywood to define, let you know of something, of how science works, how the law works, how medicine works, it's typically not. Yeah, it's not correct. Great story, it's entertaining, but not actually accurate. So we have AI has gotten very powerful. It's been around for a long time. It's over 100 years old, artificial intelligence. We've been building artificial intelligence. You can look all the way back into the late 1800s and see things that match the definition of AI. Because as it's grown in power over the years, as we've gotten more technology to drive it, it's gotten more powerful. And as it's gotten more powerful, it's intruding on our lives more. We see it more. It's been around us for decades, and we've been using it for decades as well. But because it's so prevalent, because there's this fear of Skynet and movies like Ex Machina and Her and other things, there's a huge panic around AI. So there's a lot of people that never learned AI when they were younger. It was not part of most curriculums, nor was coding or digital. They're now hearing about it today, and they're kind of taking what they've learned from what they've seen in Hollywood type things, seeing in the news, putting it together, and are very worried about it, talking about it. And AI is just a technology. It's essentially math weaponized to do statistical analysis. It's gotten very powerful because of the amount of compute we can use to do the math, the amount of data we have to find patterns in, and the complexity of the equations we can put together to find those. But at its core, it's still math. So one of the things the DoD is looking at when the DoD set up the JAIC, the Joint AI Center, a few years back, was how do we help bring more AI in the DoD? We've been doing DoD AI since the 1950s. So we've been using AI. We were one of the early Funders of AI, in fact, modern neural networks, the perceptron, as they were originally called, was created by the U.S. Navy in 1958. You can look up the New York Times article, New Navy Device Learns by Doing. And so the very first neural network. What's changed from then to here is the amount of compute. The computer that ran on had less processing power than your key fob in your car. The amount of data it was trained on was a few hundred instances of data. Today's modern large models are trained on trillions, if not quadrillions or quintillions of instances of data, and the algorithm complexity. Now, in technical term, that perceptron had 2 layers in its neural network with only a handful of nodes compared to a model today like GPT 4.0 or GPT 5 potentially rumored to have 1.7, 1.8, maybe 2 trillion parameters, depending on which number you look at. So those 3 trends that have driven this have made that AI that was working in 1958, in that form of neural network, even more powerful. Because it's useful and because there's more you can do with it, the recognition that we can start to apply it to more than just niche problems has become more apparent, and we're starting to look at doing that. So the Jake was stood up. One of their first, I think one of the things they saw from looking at kind of the lines of effort they were putting together, building the infrastructure, getting our data, clean so we can do this, and the infrastructure, hardware and software, but also the people. And they didn't just mean the junior personnel that would actually be building these models, working with these models and using these models, but senior leaders who would be, a fleet commander, a MEF commander, a combatant commander, right? Those executive level people that are running large organizations with a wide breadth of things had, in most instances, little to no knowledge of artificial intelligence. So they didn't know what it could do for their organization. What can AI do for a fleet commander? What can AI do for a MEF commander? What can AI do for recruiting command, log call? So one of the things they put in place was we need to educate our senior leaders to show what this technology is. Let's demystify it. Let's explain how it works, explain where it is useful and where it's not. It doesn't do everything. It's not magic pixie dust you can put everywhere. But let's put together an education package, and you can run our GOFO SESs, our general officer, flag officer, and senior executive service personnel through this course over time and get them smarter. They will then be hoping they will go back to their commands, one, wiser about artificial intelligence. They actually know what it is now, so no longer Hollywood level knowledge, but an academic knowledge, or at least academically schoolhouse driven. And then 2, also demand what it can do. You know what AI can do? There's not a command out there that couldn't be using more AI than they are today in the DoD. Again, recruiting command, the amount of things AI can do to help recruiting command accomplish its mission, right? Find potential recruits, reach out to potential recruits, help matches the potential recruits, help drive them through the process of get them ready to ship, and then ship them off, and you can get into that piece. AI could help with all of that, right? We do a lot of this stuff we do by hand sometimes, and we do very basic analytics. So there's ways of improving that. Doesn't always mean it's the best investment. It doesn't always mean that's the highest impact use case for AI, but educating these commanders to recognize what the technology is, hopefully would then ricochet back when they went to their command and start asking for it. I want to see more data-driven decisions. Where is our data and things like that. So this course was put together. It's 3 days right now. CDAO took over. The Jake was combined with a couple of other organizations into now the CDAO, the Chief Digital and AI Office of the DoD. And that education has continued. It's a 3-day course taught at the Naval Postgraduate School or Johns Hopkins or MIT. But it's hard to get people to go for 3 days. And it only covers sort of the 07 and above crowd. CDAO had looked at, how do I expand this out? Potentially going to the lower levels. And I took a look at the course. I'm one of the instructors for NPS. I took a look at the course and said, we can do better. We can do shorter. This is great for if you can go take an in-person, sit through a 3-day academic exercise, but can we get it down to 1 day, and can we focus it with the right story that gets to people that have zero background on AI, but just need to know how it works, which is the same thing for an executive typically, but it's also, let's focus this on, let's tell the right story. Let's walk it through in a way that you walk in knowing nothing. 7 hours later, at the end of a 7-hour day, you walk out very knowledgeable about the breadth of what artificial intelligence is. And that's where the birth of AI for knuckle draggers, as I like to call it, for math for Marines. It's like, yep, and then AI for knuckle draggers. So, hey, you give me 7 hours and I will get you smart on AI. You won't be a coder. You certainly won't know how to code or build a model, but you'll know how it works.
So what did you're saying that, we've been using AI for a long time. So, that system that the Navy built in 1958, what was that system doing?
It was able to recognize images on flashcards. So the same way we have AI that does what we call optical character recognition right now, the computer vision model that could identify your cats or identify images on the internet that started with being able to identify like the handwritten digits, numbers, letters, things like that. And this was the very beginning one back then. It's like, let's see if we can get it to tell the difference between an O and an X and a square. And can we build a machine that can do that? And it was designed to be, instead of explicitly programming it, like this is an X, this is what an X looks like. Let's show it examples of different things that it knows what it is and see if we can build those connections over time. We call neural network. We call that machine learning. Machine learning, a very old technology, even older than AI. Machine learning is just statistical fitting that we've been doing for over 200 years. We used to call it regression, other types of thing, and it's just become a buzzword now of like AI-based, ML-based AI. So it's a technique to get to AI. But that machine was designed to do something very basic and just to show that this could work, that we could build a computer that worked this way.
So I guess my next question would lead into, so, we talked about, there's probably a lot of people that remember the, prove you're not a robot on the website and do the CAPTCHA and say, what numbers are these? And it was very clearly a house number. And you were correcting those photos that were getting shown to some sort of machine learning. So how does AI differentiate itself from machine learning? Like, what's the difference?
Machine learning is a technique. AI is the end state. So there's many different types of artificial intelligence. Some of the older artificial intelligence we were using in the 50s and 60s, different terms for it, symbolic logic. We've got Bayesian statistics. There's other ways of getting to that. Machine learning is where, at its core, machine learning is defining a model, but not defining the weights of the parameters that are in that model and allowing the data to define them for us. So a very simple example would be fitting a straight line using sum of least squares fitting. So if I've got a bunch of data points that seem to be in a roughly straight line, and I want to quantify or quantifiably find out what the slope of that line is, and then where the intercept, y equals mx plus b. Machine learning is taking the data and saying, this is the best fit m, the slope, and this is the best fit b, the intercept. That's all machine learning is. And now I've got a model that I can use to make future predictions about that data. So machine learning is just in neural networks. The math is, the equations are bigger, but the idea behind allowing the data to we find the weights from using the data, and we then build a model that best fits the set of data we've got, is all machine learning is.
So is the AI kind of using those machine learned, or the machine learning algorithms that are created essentially, is the AI then using those?
So the machine learning is the technique.
Okay.
So the machine learning is when I'm training an algorithm. So I'm training a model, an algorithm, but it's okay to use them synonymously. When I'm training an algorithm, I'll have an instance of data. Right? And the current iteration of my model will make a prediction based on that data. For example, it's trying to recognize a handwritten digit. Is this a 9 or is this a 4? The model and the weights that are in it will make a prediction. If I input in, says no, supervised learning we call it. If I input in and say, this is a 9, you should be seeing this as a 9, and it's got 9 but not 100% 9. We then use the fact that it's not accurate to go back and update the weights of the model. Okay. And then we do it again. And then again, and we do millions, billions of instances of this. Each time when that instance of training data is put through the model and it's not perfect, we update all the weights a little tiny bit. So kind of like just a little tiny change to all of them, and then we do it again and again and again. And given the fact that one image is a 9, the next is a 4, and then a 1, and then a 0, and then an 8, and then another 8, eventually those weights start to converge on what we think is a model that will work on all of the different digits we've got. We can go back and test how well that worked. So that's the process of machine learning. When that is done, I now have an algorithm that can produce what we would call artificial intelligence, the ability to solve a task. The task we've built that algorithm to do is to recognize the handwritten digits. And that's what the AI is. AI is the ability to solve a task. Machine learning is how we get to that AI. One of the ways we can get to an AI.
So between the two, something like AlphaGo or Big Blue, I think was the chess one. How are those? Is that closer to the AI spectrum?
So, like, I wouldn't put AI and ML. They're not on a spectrum.
Okay.
AI is what we build. It's a machine. The way I think about AI, artificial intelligence is a synthetic device that can solve a task. Machine Often we see them as computers right now. So an artificial intelligence is that machine that can solve a task. So for the handwriting digit, what we talk, the AI is the ability to solve the task of recognizing different digits and being able to say, this is a 7, this is a 3. For AlphaGo, the AI is the ability of the algorithm to win at Go or play Go and,
Right.
and hopefully win. And you can build algorithms at Go that do different things. And that's one of the interesting things we found is you can build an algorithm designed to win as big as it can, get the biggest score, or just to win, or sometimes it'll play differently based on how we build that up, objective function. So with AlphaGo and AlphaGo Zero later, it's an algorithm designed to do something. And the AI is I've built a synthetic device, which is this piece of software that runs on a computer that can play Go. That is artificial intelligence. Okay. That is AI. Machine learning is I can build a synthetic device that can solve a task in a lot of different ways. There's a great example of it's in the Computing Hall of Fame. Danny Hills built a synthetic device that could solve the task. The solving of the task was playing tic-tac-toe instead of Go. He built it in Tinker Toys. So it's you look at it, you can see it. The human goes first, then the machine gives its counter move, and then you play it. The machine will never lose. It'll always play tic-tac-toe. If you make a mistake, it'll win. But if you play perfectly, it will play perfectly too, and there'll be a tie. So that's a machine that can solve a task. That is AI. That AI was built with not machine learning. It was built by a human putting, expert rules-based system, we call it. Other ones are, okay, cool. I don't have the ability to sit down and write down all the potential steps of a Go game. I want to build an AI that can learn to do that itself. And so I give it lots of data, which is what games look like and how different moves in the game lead to whether you've won or lost, and do that and then program that in. And the way we do that quickly is to do lots of iterations. That's the machine learning piece.
Yeah, I think later versions of AlphaGo and AlphaGo Zero actually played itself to build up that data set.
They all did. So AlphaGo was initially trained on thousands of human-played games. Here's a bunch of instances of how humans have played Go. Use these as your training set, leads them to start to learn the rules of Go and what to do, and then allowed to play itself as well to improve. AlphaGo Zero, the zero means it had zero training data. AlphaGo Zero, I played on 0 human games. It was basically given the rules of Go and allowed to play itself from the very, very beginning. So initially it was terrible. Over time, it started to find that certain pathways, certain patterns of movement gave rise to better outcomes and winning. And playing against itself, it rapidly iterated to get better.
Yeah, I think the thing that was most interesting was that story is you could actually see, as it was playing those iterations, you could actually see, the historical portions of like, oh, this is about the same time that this particular set of plays or this strategy was very big in Go historically. Mm-hmm. And then it left that and moved into, and it almost followed directly the historical rise of different strategies within Go. And you saw the same thing in AlphaGo Zero as it played through its games. So I found that very interesting from that standpoint.
And that's kind of how learning starts when you start with zero knowledge, right? You experiment with something, you fail. Experiment with something, you fail. And every failure in science, there's no such thing as failure in science. Like every experiment teaches you something. If I knew an experiment was going to work, it wouldn't be an experiment. So we do an experiment to test a hypothesis or to test something. So if the experiment works, we validated something. And if the experiment doesn't work, we validated something else. So every experiment leads to more knowledge if you're setting up right, if you're doing the process of science properly. So the same thing when you're allowing these games to play, it's like they're learning, okay, try this, doesn't work, try this, doesn't work. So they're enabled to do that with billions, trillions of iterations because we can let them run, at machine speed. So they learn over time, and then they start to learn more broader concepts that gets embedded in their weights. And it was interesting in Go, AlphaGo, whereas chess was solved in 1997, where IBM's computer was able to beat Garry Kasparov. When the field of artificial intelligence was first given its name in the 1956 Dartmouth conference, when they're like, hey, we need a name for this field of sort of building machines that can process information. And Herb Simon wanted to call it complex information processing. That's really what the field is, right? AI scares everybody. Complex information processing is really what artificial intelligence is. And Herb Simon said we should call it complex information processing. John McCartney's like, no. We need government funding. ARPA at the time is going to give us money. We need a cool name for this. Let's call it artificial intelligence. And Marvin Minsky, even at the time, said, this is a bad idea. This is a bad name for it. Intelligence is a suitcase word, he called it. It's a word that brings with it a lot of meaning packed into it like a suitcase that you didn't intend it to bring. If you look at the Wikipedia definition of intelligence, it basically defines what we would think was a human intelligence, or ability to reason and understand context, and a lot of things that machine intelligence is very different. Machine intelligence does not work like human intelligence. But at that conference, they thought, kicking it off, they got the funding, off we go. They thought they'd have chess solved within a year. We can build a machine that can play chess and win at chess. This shouldn't be that hard. Turned out to be 40 years later before we got to that. But after chess was solved, the Go people, the Go community was like, well, you're never going to solve Go. Like, this is a way more complex game. Chess is relatively simple. Go's got almost 100 order of magnitude more sets of moves. So much more permutation space for a computer to work for. No way can a computer learn how to do this. You just can't program it. This is a human thing. So DeepMind, challenge accepted. They went after it with AlphaGo. And they ended up building it, and they challenged the Go community. The top player, Lisa Dahl, would not. He's like, nah, this is too easy. Ended up playing somebody else. They beat the other challenger, not top tier player, but they beat somebody else. And then, okay, fine. They set up a 5-game match with Lisa Dahl. He lost the first game, but there was a lot of like, well, okay, I wasn't kind of paying attention that much. Sort of like, all right, it did bring my A game, right? Casey at the bat. I let the first pitch go by, so now I'm going to bring my A game. So on the second game, everyone was a lot more like, okay, you need to really pay attention. And an interesting thing happened on something called Move 37, a very famous move. Move 37 at the time, AlphaGo was considered to be a terrible move. Everybody looked at Move 37 and said, aha, that move is terrible. That move sucks. We have still maintained our pantheon, at the top of the intelligence here. We figured out to do this. So everyone looking at this, and this was all the people watching and the people analyzing, and we'll come back to what happened later. Turned out by the end of the game, as the game progressed, it turned out Move 37 was brilliant. Like, so brilliant, nobody recognized it at the time of how brilliant it was. It turned out Move 37, playing later on, ended up, AlphaGo was able to beat Lisa Dahl second game in a row. The match ended up finally 4-1. Lee was able to win one game. And looking at that second game later on, people have looked at it, and this was one of the interesting things that we saw. People looking at it was like, that's a move from a strategy no human had ever played before. No one had ever seen that. And this is an interesting thing when we get into artificial intelligence about how we're going to use it in life. AI does funny stuff. AI produces garbage all the time. You've seen this in ChatGPT. You see this with Google Maps. Sometimes Google Maps, which is AI, would send you to London and have you drive across the ocean. You're like, well, how can this be so dumb? And it's like, it doesn't have any context of what it's doing. It's solving for an objective function. But we've seen AI do dumb stuff, but sometimes when it does something like this, how do we recognize that it was very brilliant? Nobody recognized that was super brilliant. So if we start to build AIs that help us in the warfighting capability and help us with this stuff, how do you, when you say you as a human you have the final say, like it's your responsibility to accept the decision or the recommendation of the machine, how do we start to teach people when to recognize something that's so brilliant versus something that's stupid? And that's where, as we get an AI that can help doctors, and a doctor's like, that seems dumb. Like, AI finds a much more powerful, a much deeper pattern that we didn't see, and recommends this course of action. And a doctor's like, I've been doing this for 20 years, no way. Vice, when do we trust it and say, wow, that's a brilliant insight, we should do that, right? For Move 37, at the time it was, that's so dumb. It would have been my assistant helping me play Go, and it recommended that move. Most professional Go players and most serious Go players would not have done it. They would have done something else, and they would have ended up losing. So one of the things we talk about in AI for knuckle drivers is this kind of vignette. And also, what does this mean for how do we build warfighter trust? So one of the RAI implementation pillars of trusted AI that we're going to deploy in the DoD is how do we get the warfighters to trust the AI that we're deploying to help them? And AI is not, it's a decision support tool in the same way. Google Maps helps you navigate around. You still drive the car, you're still turning the wheel, but Google Map is handling that, what the AI is good at, of navigating you around a city and finding that route so you can focus on what you're better at, which is driving the car.
Yeah, I think there was one a couple of years ago. They're doing some experiments with AI, and the Marines basically got inside of a box and moved across the street while wearing the box like Metal Gear Solid.
Another DARPA. DARPA brought its top AI experts, the top AI research team, to go head to head with our finest Lance Corporals So in a battle of wits, and Marine Corps 1, DARPA 0. So, and exactly that, it was DARPA built a computer vision model, an AI running on a camera designed to detect whether a human was walking through the frame. And this is obviously of great importance to us. You look at Afghanistan, Iraq, or any of these distal bases. How do we use AI to help us augment base security? Whether outside the fence line, inside the fence line, in buildings, how do I use it to put on camera to detect when a human's there? Basic motion detector can be set off by a squirrel or a blowing tumbleweed. How can I build a more sophisticated AI that can differentiate between, nope, that's a squirrel or a dog or something walking on the fence line, between, yeah, that's a person. And then to alert a human security operator to be like, hey, there's a person walking there, go double check. So they built this model, and the Marines showed up. One of them was successfully completed it by somersaulting through the image. The AI was trained to recognize people walking. It was not trained to recognize somersaulting. So its training data had people walking in different ways, but it didn't have anyone somersaulting. So one Marine beat it by somersaulting. Another walked up to it with a tree branch, very Looney Tunes style. And the model was trained on a bunch of instances of normal people walking, not one carrying a tree. So that threw off the model. And this is one of the, we talk about AI being, people where AI is going to take over the world. And this is not how machine intelligence works. Machine intelligence has no context. It's very powerful, but in a very narrow sense. So I like to think machine intelligence is narrow but deep. And that narrowness leads to brittleness. That narrowness leads to, you get it slightly, just a tiny bit outside what it was built to do, and it completely fails. Or gives results that sometimes make no sense, but that's just the way the math works. On that example of an AI built to recognize the 10 digits, 0 to 9. The way the math works, knuckle draggers, we walk through how a neural network, this exact neural network would work. If you were to give it an image of a cat, you can see that the math equation will solve. The output of the math equation is something, 10 different nodes that can populate between 0 and 9. So it's going to tell you your cat looks like a 4 or a 2. And what you'll see in the press, or people don't understand AI, will be like, I gave your AI that was supposed to recognize numbers 0 to 9 a cat, and it said it was a 4. It's hallucinating, or it's doing something like that, or it's dreaming. It's like, nope, the math was not built to recognize a cat. This AI was built to solve a task. The task it was built to solve was recognize the digits 0 through 9. Not cats, not hot dogs, not letters, upper or lowercase. You gave it an instance to do something outside of its training. That's user error. That's you not understanding what the model was built, and then you're assuming the AI doesn't work because you didn't know how to use it. So this is one of the things, reason we put courses like the course like Knuckle Draggers together, is to understand that this is a tool. Here's how this tool works. A lot of the silliness you see in the press and the silliness you hear on kind of like in the chattering about AI, it talks about this. This is people that don't understand what's going on, and they're laughing at it, or making fun of it, or they're kind of like just extrapolating, aha, I told you so kind of mentality. But the reality is, here's how it actually works. You come out of Knuckle Draggers, and you those myths, and like that lack of understanding, no, you should know it. And if people come out and say, okay, I get it. And I've had people come back and say, yeah, I saw this article where they said this. And it's like, now I understand where that person read that newspaper, the writer there didn't understand what they're talking about because they completely got it wrong and were saying this. And now I got it. All this was a sample, distribution problem, a sample size distribution problem. So
as we talk about, feeding in data, I think I read about a study once that they were training it to recognize wolves.
Yep.
And what they found is they were getting a lot of hits for scenes that had no wolves and no animals whatsoever, but they slowly realized that what they had accidentally trained the model on was snow instead of dogs. So how important, I think we've run the spectrum a little bit here of, hey, we're going to feed it a bunch of data, and then you have something like AlphaGo Zero where we feed it no data. So if we're feeding data, how important is it to make sure that we have the right data? And how do we know if we have the right data? How do we decide, okay, I'm not going to feed this thing data at all?
I think that's the critical piece when it comes to understanding how AI works. So modern statistical-based AI, machine learning-based AI. Machine learning is the technique. Statistics is the math we use to understand the technique. Modern statistical-based AI finds a pattern in data and finds a pattern in historical data. That pattern is reproducible. We can use it to predict the future. So if I can find the pattern in 1,000 or 1,000,000 images of the difference between a wolf and a dog, the example you're referring to, okay, I find the pattern. Wolves look like this, dogs look like this. I found that pattern between the 5,000 wolves, the 5,000 dogs. I can use it to make future predictions. That's how AI works. Now, when we put in that data, and we use the way the math works, again, that computer vision model, if you're not being careful, it doesn't know there's a wolf or a dog in the picture. When you ask a person, what am I looking at? They'll see a dog. They'll see a wolf. They typically don't look at the background immediately, right? They'll be like, what is this an image of? And they'll say, it's a dog, a wolf. I'm like, what about the tree in the background? Well, yeah, there's a tree there too. I thought you meant the most, the prominent feature of it. The AI doesn't know that. All it knows is there's a box with a bunch of pixels. And the pixels, the math, the algorithm does math on those pixels and outputs an answer. In the wolf versus dog example, most of the pictures with wolves had snow in the background, and very few of the pictures of dogs didn't. So just like a kindergartner learning to associate, all the pictures of wolves, I don't know the difference between a wolf and a dog. I can't tell. They all have ears, a nose, a tongue, but all the wolves have a white background. Maybe that's the pattern I'm supposed to be secretly seeing. So kindergartners pick up on this sometimes too, and they'll be like, "Oh, it's got snow," and you're like, "That's, you were supposed to look at the wolf versus dog." I'm like, "Well, they didn't know that." They're too, the brilliance of ignorance sometimes. So what happened was the AI learned that feature. So the way we define these features is these 5,000 are this, and the biggest difference between the two is the ones with white. So then when you take that exact algorithm and you show it the next image, the white is what's setting it off. White means wolf, right? Not ears or nose or brow or eyes or different. People are like, well, it's the shape of the nose, and say all these things that are not necessarily what the difference between a wolf and a dog are. You basically train that algorithm on wolf. White meant wolf, not white meant dog. And that partly comes from the data we put into it, because we had bias in our training data, so that we found a inherent bias in there. So part of working with AI, machine learning based AI, statistical based AI really, is building models, and then you understand the bias that might be in your data. One of the things I talk about, the field of artificial intelligence came from the field of data science and operations research. Are you familiar with the example of the bombers in World War II?
Yeah, with the bullet holes.
Yep. So if you're not, the bombers in World War II, we'd send bombers off to bomb the enemy. They would come back. Not all of them would come back. Many would come back with bullet holes in them, and they asked people to do a statistical analysis of where the bullet holes are to try to figure out where should we put the armor. And they found that many of the bombers that came back, or all the bombers that came back, they had very few bullet holes in certain spots. So the initial thought was, well, that's where the armor should go, or put the armor where the bullet holes are, or they're getting shot. But it turns out then you have, what you're looking at is survivorship bias. You're looking at the set of bombers that made it back. You don't have any bombers that made it back if the bullet holes were random, statistically random. Why don't I see any bombers with bullet holes in the engines? So it's an indication to me that the bullet hole in the engine may be fatal to the bomber. I should put the armor where the bullet holes are. That was the beginning of the field of operations research, really, in its most modern form. I like to trace their lineage back to that moment, like us in Twin Tavern. And so that grew into that. Cool. I got more data. But that was the first thing I understand is I don't have all the data here. I only have a subset of the data. That wolf versus dog image wasn't every picture of a wolf that existed. It was just some of them. So that's absolutely critical as we build these things to understand where that bias is, to think that through. And that's what a good data scientist does. There will always be bias in statistics-based AI models. You cannot get rid of all of it. What is more critical is to understand what that bias is. What we want to do is you understand what the bias is. Well, on the range, we don't use Kentucky windage. We do use Kentucky windage when it comes to AI. So if I know my model is biased one way, got it. That may be, I can't use it for that use case. So we want to understand the bias that's in it. We want to minimize it as best we can to try to keep the bias out of it, but also recognizing what bias is in there. And looking at a model, if the bias is fatal to the use case, then we can't use the model. But if the bias doesn't impact the use case, or we can mitigate that potential, that's one way to deal with it. Google Maps will occasionally tell you, not anymore, but it will occasionally tell you to drive in the ocean. How do I mitigate that AI? I make sure the human's actually checking it and doing the driving. Okay, so now I've got an AI that occasionally gives me a bad answer, like a really stupid answer, but I can use it perfectly well because I've mitigated the way it fails by having a human in the loop. And there's another example we use in the course. It was called giraffing, about how bias can creep into the data set we use to train an AI off of. Same very thing. There was random pictures were showing up as giraffe frequently, a model that was trained. And it was like, why? And a lot of the pictures of the giraffes were taken from the Serengeti and the African safari type imagery. When you look at, okay, what are the pictures I've got from African safari? I don't have drones flying around picturing everything. I've got a lot of tourists taking pictures of, or tourists take pictures of, which is usually like photogenic stuff. But taking pictures of giraffes and lions. There aren't a lot of pictures of like lion dung and giraffe dung. So a lot of my data sets got these, more of these giraffes in here. And those are also the pictures that get saved. So my training set's got an over bias on giraffe. And if I use it to build a model, your algorithms might see things that are, they might detect things that aren't there. This is critical for us, especially for instances of data that are charismatic, but in reality exist very infrequently. Many of the pictures of stuff on the earth do not have a giraffe. But we've got a lot more pictures of giraffes than we probably should, because there's so many people taking pictures of them on before. If you train a model with that bias, you got to recognize that. And there's ways that data scientists work with testing their models to see if that bias has crept in, and then how do we fix that. But it was a very interesting one on some of these early computer vision models of like recognizing even that inherent bias in the data. Because like the bombers and like everything else, we don't train our models on all the data that exists in the universe. We take a subset of the data. If we're not careful about understanding exactly where that subset came from, we can introduce bias in ways we didn't understand.
Yeah, so one of the questions I wrote down at the very beginning is it actually intelligent?
No, that's the thing about that word. Again, an artificial intelligence is a synthetic device that can solve a task. That's all it is. The tasks can be very simple, or the tasks, as AI has gotten more powerful, the tasks that AI can solve have gotten more complex tasks it can solve. But it doesn't have intention. It doesn't have emotion. It's not alive. Like that's the word with that suitcase word of intelligence. That when we say an animal or a person is intelligence, we ascribe a range of things to it. Emotion, it's thinking, it knows its context, it may be trying to have some internal self-awareness, consciousness. The artificial intelligence we build are just equations that can solve a task. Here's some input data, run it through an equation, and output something. That doesn't have intention other than what we've built, the way the model's been built. It doesn't have emotion. So that's the word of complex information processing, better term than artificial intelligence. But I don't think we're going to change, and we're not going to change the name of the field most likely at this point. One of the reasons that I put together, it's one of the very opening of Knuckle Draggers is like, look, this is what people, when they say intelligence, cool, let's talk about the difference between machine intelligence, which is what AI is, and human intelligence, and they work very differently. Again, human intelligence is broad but shallow. So you can put humans in a wide range of situations and they can take care of stuff. Machine intelligence, very narrow, very deep, incredibly narrow. So not the way we normally think of as an intelligence, which is where machine intelligence works very differently than human intelligence. And as soon as you start to recognize that, you just go, oh, that's all AI is? All AI is our ability to put together math equations that have found a pattern in pre-existing data that if that pattern is reproducible and exists in future data, we can use to exploit it.
So I think I was going to ask about the Turing test.
Mm-hmm.
Would we have to, right now, would we have to train an AI that could specifically try and pass the Turing test?
So we have AIs that can pass the Turing test.
Yeah, okay.
So ChatGPT can pass the Turing test. It's good enough now, most recent versions, to full humans. But this goes back to when we were starting this early field. And Alan Turing had talked a lot about machines that could think. And one of the things he realized is, I don't know if a human can think. I don't know what I could ask a human for them to prove to me that you're a conscious person, right? That's a very famous example from philosophy, that we could all envision a world in which we are the center of a simulation and everything being presented to us as a simulation. You can't actually disprove that theory, right? It's very hard to disprove that. It's like, okay. So Turing was like, I don't know how to prove intelligence then. So I can't prove if it's intelligent or not. So I'm going to pick an action. I'm going to have it demonstrate an action to me that I can test. And if it can pass that action, I'm going to say it's passed the Turing test. So it wasn't an IQ. It wasn't doing that. It's like the ability to solve this task. Have a conversation with me, or have a conversation with a person. The original Turing test, I think, was set up as like you're talking to two separate people. You are the tester and you're talking to a human and an AI. And if you can't tell the difference between them, or the AI can fool you into thinking it's a person, it's past the Turing test. But Turing didn't have intelligence in it. That was more a marker of we've passed a certain threshold in computing, where we've got a machine that can imitate a person. And that's what the original game for the Turing test was, the imitation game. So, and it was like, hey, can I build a computer that can imitate a human to the point where I can't tell the difference between the computer and the human? Doesn't mean the computer's alive, thinking, motion, intention, has judgment, context, faith, any of that stuff. All I've known is it's an action I've defined. It can imitate a human in this particular task. Which is where now that we're rethinking this, we're like, all right, well, now that we, for a while, being able to win at chess was considered the mark of intelligence. If we can get that will have to be a computer that's what we consider like human intelligence as opposed to machine intelligence. And then we did it, and you're looking at this, and you're like, that's just math. And the same thing with AlphaGo Zero. And you're like, well, it's just math still. Now you've got being able to pass the Turing test, and it's like, no, it's just still math. Okay, we need the next test for that. And we'll probably do the same thing, and we'll pass it with something, and it'll still be just math. So
now that you're saying that, all those captchas that we do to prove we're not a bot when we log into a website, are those actually useful then if we're being able to train all these AIs to pass things like this, image recognition? And
so there's a couple things on those. One is, depending on exactly which one you're looking at, there's one where you kind of just click the button. That actually works by, it's kind of checking your mouse movements. Humans jitter tiny little bit. So the way a human moves a mouse is different than the way a program would move a mouse. So it's looking for minor variations. Like when we do a facial recognition algorithm, you do your iPhone picture, one of the things that's built into that AI, it's looking for, it's called a liveness test. So it's how do I know it's not just a picture of a face put at me, right? Vice an actual face. And there's two ways to do that. One is to try to capture some level of 3D-ness. The other is to look for liveness, so liveness detection. So in the 3D thing, I can fool with I can get a 3D model of somebody's head to get them to open a screen. And if it's doable. Somebody's job somewhere to break into something is put together a 3D head that can do that. So the liveness test looks for micro movements in your face and your eyes and things like that. And because if the completely static image, the algorithm would detect that as, the camera's pointed at a picture, it's pointed at a mannequin head, it's pointed at something that I'm not seeing move. So it's looking for that micro, and it's such micro moves you don't notice it. So similarly with that CAPTCHA, is looking for very minor changes, very minor differences in how a human would move a mouse, and we all have a little jitter in it versus a computer. The other ones with the images are two things. One, this is one of the ways where we have people labeling data for machine learning training. So you are doing free labor for them every time you log into one of those. And I always like, so identify all the images with a bike or a stoplight. And you're like, am I training a self-driving car algorithm here to like recognize different things? And you absolutely are, most likely. So there's that. And there are also images that a couple of things. One is an image that are poor, that algorithms are poor at, or images that they failed at before. Or for whatever reason, it's like, why does it always get this wrong? Let's send this to the humans to get some human reinforcement learning with human feedback on this. And you go, that is a bicycle. Yep, that's the one with the streetlights in it. And then they capture that back. So those CAPTCHAs are absolutely that. They're using human cognition to sort of help the machines learn. And differentiate between a machine looking at it, which would be not as good at it yet.
So we'll cycle back a little bit to you touched briefly on the human AI interface. And I think this is the big piece where, there's been a lot of talk about, hey, we're going to take these UAVs, we're going to launch them, and we're going to let them make decisions on weapons release based on hitting certain criteria. And so there's that conversation of, and you brought it up a little bit, is that interface between humans and AI. Because I think from a military standpoint, that's going to be the biggest thing for us, is making that ROE decision and where do we accept risk.
Well, I think you're absolutely right. And I think this is something we do very poorly right now into thinking about this. This is one of the things we cover in Knuckle Drivers when it comes to autonomy. We launch UAVs all the time and allow them to make lots of decisions, right? So ways to think about autonomy is driven by AI. So machine autonomy requires machine intelligence. Machine intelligence is by definition artificial intelligence. So any form of automation or autonomy requires some form of AI. How we built the AI is irrelevant, but the task the AI is going to solve to enable that autonomy is what we're worried about. So we may have AI on an autonomous system that's monitoring the engine for, predictive maintenance purposes. That's an AI. It's probably running in human out of the loop mode, right? So it's essentially the AI equivalent of your check engine light for an autonomous system. perfectly fine, right? That doesn't, usually people don't get upset about that. It's not what they're talking about. We have AI that might help the thing navigate from point A to point B. We have AI that can help. That's a very particular task. We have AI that might help it keep on a straight and level heading, right? It gets a gust of wind, it gets blown. AI keeps it flying and it's able to do this in flight parameters. We may have AI that's able to actually manage the sort of like more detailed pieces of that flight envelope as well, keeping the wings level and keeping it as it navigates through a turbulent air. We may be perfectly fine with that. We've got an AI that's running in autonomous mode, right? We've given it a random waypoint to get here. It may have an AI that can navigate itself around threat environments or have some picture it knows of enemy or surveillance locations, either by optical, sound. Hey, get from here to here, but avoiding where you think there might be a microphone listening for you, people looking for you, and it'll then plot that course, much like Google Maps does for you. Get me around the traffic, please. Get me around, get yourself around the obstacles where someone's going to find you. Get to the target and let me know when you're there. So we've enabled that level of autonomy, right? So we've got all these different slices of a task that an AI is solving, and they're not the same AI. That's one of the things about people think we're building a big brain that flies an autonomous system. We build them very individually. Your car's got hundreds of AIs on it doing very individual, discrete tasks. When we look at that, we go, okay, fine. I'm fine with the AI looking at, monitoring the engine. I'm fine with the AI doing some of these other things. But the commander's risk assessment is, what am I going to have a human in the loop, on the loop, or out of the loop doing? With the monitoring of the engine, that's a human out of the loop. When it comes to target identification, I'm okay with an AI identifying a target. Right? Cool. You flagged a target for me as a human operator or human overseer. Let me go see what you found. Nope, that's a hot dog. So, and that's where the AI will identify the target, and it should pass that back to a human and say, I think I found a target. Do you think is this the target of interest? Is this something, right? So, and then we validate that and say, yep, you've actually found 3, say a Ukrainian drone, you found 3 Russian tanks moving through a field. Perfect. Tank. All of them are tanks. Or maybe you found 2 tanks and a tractor. They just happen to be moving by, and you're like, no, those are the 2 tanks. But we keep that human in the loop to make sure that we haven't even gotten to the weapons release piece, right? Because the weapons release decision that's very human. So where the human sits in the loop based on a particular task should be different, and our rules of engagement and our policies should probably reflect that understanding of how artificial intelligence actually works and is built, so that we can build it in a sense that I don't need the AI I've got monitoring the engine on a UAV should have a different certification process and oversight than the AI I've got selecting the target. And where is not only is how the certification, and then where is the operator in the loop to validate what the AI, the machine's recommendation is. The machines make recommendations. That's essentially how to think about an AI. It solves a task. What it solves is makes a recommendation. If I plug it in and allow it to then act, now I've built in autonomy. Right. So the tic-tac-toe playing computer, does it move the piece, or does it tell me where it thinks I should move the piece? The recommendation, and I choose to accept it or not. The same thing with chess. Deep Blue and AlphaGo didn't actually put the piece on the board. They said, put a piece here at this square. And you go, okay, cool. I will take your recommendation. So those were very human in the loop types of uses of AI. Understanding exactly where the human sits in the loop. So it's going to be one of the axes along which we look at risk, right? Because the more human in the loop we have, that's one way to mitigate risk, right? A human out of the loop AI is much riskier. We have to be much more sure of what it's going to do. And if it's just having the check engine light come on, okay, I'm okay with that. I don't need to be monitoring that until the light pings on. But other things I will want to pay much more attention to. I much want to have that human in the loop. And the second thing is, the second axis is, what's the AI doing? What's the task it's solving? Some tasks are they're not dangerous or minor. I don't necessarily need to be monitoring that. We have AI that can do, change frequencies of how it's communicating and all that. That's a relatively minor task. And if it fails, there's no necessarily risk to life. There may be some risk to mission, but if I've got multiple backups and things like that, where that targeting piece, people are like, you're using AI to identify a target. You're like, I'm using AI to make a recommendation of what you think a target is. Whether the human accepts that or not is the next piece. And a lot of times people then conflate that, what the AI is doing with the human in the loop construct with, well, the humans are just accepting the target. That's not an AI problem. That's a person problem, right? That's a human problem. We've looked at targets all throughout history and said, I'm going to shoot that thing. You're like, are you sure? You have your glasses on here? Like, are you sure that's a target? And you're like, it looks like a target. It's moving. Right. And this has been a known problem And we have procedures to address that piece of it. So it's not an AI problem per se. It's how do we train the human to make the right decision when it comes to warfighting, whether I have the legal basis to engage with force. Should I engage with force? Is this the right time to do it? Or do I want to like wait 10 minutes and see what happens? And before we, announce that we can track this, there's a lot of things that go into that, but people sometimes conflate that with an AI problem. You see this a lot overseas, some of the overseas wars. People, oh, the AI is making the target selection and humans are just blindly accepting it. I don't know that to be the case. Like, but in the humans making the acceptance choice, it's training the human to understand what the algorithm is telling them is where we have to make sure we get right. And that goes back to training a human. It's like, hey, if that picture says there's a giraffe, we know there's a problem with giraffing. This one particular thing, if it says giraffe, double check it. Like, it's fine if it says hot dog and cat. We know that hot dog and cat, it usually gets right, but we've actually looked at how it fails. And if it says giraffe, double check it, because we get a lot of weird giraffes. So that's how we train an operator to understand how AI could fail. And then when we then use that, these are some of the pieces of the mitigation that we put in place, like understanding where the human is in the loop. What is the particular task we're looking at? How has the human been trained to understand where the AI is and isn't good in this particular use case? And all that can be rolled into a decision for the commander about how to employ that AI, right? If he or she's comfortable with different use cases and different mitigations, and that's how we do all of our ORM. Okay, I'm looking at this, and we have an ORM matrix, and we go, what's my next step to mitigate this? If I'm looking at this, I'm not comfortable with the risk we're taking. How do I mitigate this? Do I retrain the algorithm? Do I go from a human on the loop to a human in the loop, where I need to make positive control before it takes action, not just, like human can override it if they want to, but if nothing, they don't do anything, it happens. That's the risk matrix will allow for commanders to make those decisions about how to employ that AI.
So we're closing up on our hour. So I've got two more questions. Sure. The first one's going to be, we're going to tie back to the very beginning with Terminator and our discussion about Hollywood and their view of AI. So
awesome. Sounds fun.
Is there any shred of evidence? We've talked a lot about in the last hour about what AI is, what AI isn't, what it can and can't do. Do you foresee a path or any evidence to suggest that we could get to something like Skynet or HAL or these dangerous AI that you could argue that those are more of what what we were talking about with human intelligence, with emotion and forethought, if you will, to go into their learning. But as we've established here, that doesn't really exist in the AI that we have now.
No, and I think a lot of things get conflated. So there's a long running, humanity's for thousands of years has had a myth that we're going to create something that will destroy us, like the creation myth, right? So whether it was the golem or whether it was Frankenstein or whether it was other things, it's just something that it's a myth we keep to, that our hubris of trying to play God or trying to, be bigger than we are above our station is going to bite us in the ass, right? And so this has just been a long running thing, and it changes from decade to decade and century to century about what's going to do it. Magic, nuclear weapons, Frankenstein. And often, usually the newest technology that most people don't understand becomes that myth maker, right? So when electricity was invented, nobody really understood what it was. So you're like, I don't know what this stuff is. It's really weird force. What if we just zapped a dead body with it? It'll bring it back to life. So we got the Frankenstein monster, right? And then you're like, that's not how electricity works. And then you got into radioactivity, right? So radioactivity, the same thing. We would know how it works. So people are like, maybe we should take baths in it to get better health effects. Turned out not a really good idea. But you're like, maybe it can give you superpowers. Spider-Man first got his powers by being bitten by a radioactive spider. And then we realized that's not how radioactivity works. Getting bit by a radioactive spider wouldn't do anything. So in the 90s, Spider-Man was then bit by a genetically engineered spider. So, this new other technology we don't understand. We'll just let it be a stand-in for magic. So the same thing now we are kind of with this AI, right? Nanotechnology at one point, a couple decades ago, was very much that. Nanotechnology is an interesting one. But then same thing with AI. I don't understand how this works, so it's going to become the magic that gives rise to this monster somehow that does it. And we get our comeuppance as trying to play God above our station. So when all these questions come up, it's helpful to level set back to that, because some of these questions have been around for 5,000 years. And if you're going to make the same comment that's been made for 5,000 years has been wrong for 5,000 years, you got to have some extraordinary evidence to say it's different this time. People are like, well, is AI going to make us dumber? Like I've been hearing that argument, not personally, but it's been around since Socrates. Socrates didn't write anything down, right? He didn't believe in writing. He thought writing would weaken the mind, and that the act of writing things down was weakening the mind. You should memorize everything. So you want to tell a story, memorize it. So this whole newfangled stuff with all the kids writing stuff down now, the kids they're weak. They're going to grow up not being able to think and remember things. So it's an open question as to whether you think society's better off 2,500 years later than we were. We've been to the moon, we've done a lot of things, but Socrates said writing was going to destroy humanity. Very similar argument. You probably pick any decade, century, and do the same thing. So you see some of these arguments and you hear them, and before you even answer them, you got to go, I've been hearing this for a long time, and it's just, you just replaced with the most modern bugbear, the boogeyman that goes into it today. But it's still, maybe at some point it's going to be right. So when you look at something like a Skynet, you're conflating two things. One, the ability to build a very powerful AI that can solve multiple problems, like in a broader sense than just a very narrow intelligence, but also giving it some sense of intelligence, some sense of emotion, intention. Why would a super smart AI want to take over the world? Why would it have that motivation? Humans have that motivation. Some humans have that motivation to rule and do that. Why would a machine? Why would a machine want to do anything? Right? Like, where would it get its intention from? Where would it have emotion? Would it have all that? So that's where all of a sudden we've taken these concepts of intelligence and said, well, it's going to be like a human brain, right? You're like, we don't even know how a human brain works. And you dumped it onto a giant processing power that's enabled to solve very complex chess games or Go games or StarCraft or poker, because you've got AIs that can do. So that's where you conflate those two. So to me, this is one of the sillinesses of AI, is to look at this and not understand. When you look at the math, you're like, okay, that's not a real risk. There are real risks to AI, right? There are real risks to building very powerful pattern recognition engines based on historical trends, right? Because that data all comes from history, and those patterns don't necessarily repeat themselves. One of the reasons we see bias in a lot of this is because the world has bias in it. So we try to correct that bias. Often our corrections introduce their own bias. It's very hard to kick bias out. So there are real risks to AI. The joke in the AI world, one of them, one I like, it's not that computers are going to get smart and take over the world. It's that they are dumb and already have. All right. And you're like, people are worried about smart computers. It's like, that's not the problem. The problem is we've got all these computers out there that are taking care of these things and handling a lot of the AI that's going on right now. And they're all completely stupid. Like, they're very narrow things. They have no context. They don't understand the context of what they're doing. There's a very famous thought experiment from Nick Bostrom at Oxford. I was talking about like the real risk, potential risk of AI, a little goofy example, but it's like, what if we built an AI machine that's job was to make paper clips? We gave it the objective function, the math it was to objective to optimize to, of making as many paper clips as it could. And it just was so intelligent, no emotion, no intention. It was just really good at figuring out how to make paper clips. And it was able to be like, I can take all the mass in the earth and make paper clips. And then recognize it's like, oh, these little humans here, make sure I got to turn them off. They could turn me off. So if they turn me off, I can't make paper clips. So the route to making the most optimal number of paper clips is to not let the humans turn me off. The easiest way to do that is to eliminate them, use their bodies for more paper clips. Right. And then keep making paper clips until you essentially take all the mass in the universe. It's clever enough to figure out how you get off the planet, basically turn all the mass in the universe into a giant pile of paper clips. So is this something to worry about? Kind of. And this is called the AI alignment problem, right? It's that building these things, they solve very discrete tasks and they're very stupid. Like that machine building paper clips had no concept of humanity. It was just designed to make paper clips. This is Mickey's Fantasia all over again too. And this is very similar. We call the AI alignment problem. It's very difficult to define exactly what you mean. Often when you ask for something, you don't ask for exactly what you want. You ask for something assuming there's an understanding of like the context of my question. This also famous stories throughout history. King Midas asked for everything he touched to be turned to gold. He got exactly what he asked for, right? But when he asked that, he would have said, I thought you meant that you probably should have gotten the context of I didn't mean the food or the water or my family. Same thing with, we have stories like this when it comes to genies in a bottle and all that stuff. So with AI, they are dumb. We are going to get exactly what we ask for. So part of the AI alignment problem is how do we define exactly what we want? And we've seen AIs that solve problems in very interesting in ways we did not expect based on the rules that we've built them, especially a lot of computer games have weird glitches in them that AIs have been able to find. One great example is we trained 2 separate AIs to play Tetris. In one, we gave it the objective function, the goal of optimizing its score. You get more score by more bricks, so the longer you can go, the higher your score. The other one, they weren't really thinking, they gave it the objective function of never lose. To get to the same thing. You're like, you never lose Tetris by continuing to just get all the bricks until you just go forever. The game also there's another way to play Tetris and never lose that it found, that maybe a 10-year-old, 10-year-old in a bad mood probably knows as well, which is to press pause right before the last block is about to kill you or end your game. So the AI learned to do that as well. And now we've got an AI that did exactly what we taught it to do. Learn to play Tetris and never lose. And it's never lost at Tetris because it now knows how to, it can always pause. If something's about to go wrong, it's got the pause button. So when we build these AIs, we build them to be very careful and thoughtful about exactly what we're optimizing to, which tends to make it interesting as to how we're going to employ them. So you have to be able to define exactly what you want very carefully and very clearly. And so that's, I think, a more real fear vice, like Skynet's going to take over the world. And John Connor's going to have a conversation. It's like, well, you or the Matrix, we just got annoyed with you. Computers don't get annoyed, thank God. Like, we get annoyed with them. But
I mean, I, for one, welcome our new Paper Clip
Yeah,
Overlord.
I do too. Yeah, it just ends up in someone's training data. Hey, I'm on your side, right?
So, sir, the last question I'm going to ask before I turn it over to you for closing comments. You've made a couple mentions of the Knuckle Draggers course. If folks are interested in attending or finding more information about Knuckle Draggers, how do they do that?
Reach out to me. It's something that it's a course that I teach both in DC but also across the country. I've taught combatant commands. I've taught both coasts, up and down, north, south, east, west. So it's a 7-hour course. A lot of commanders have asked to come in. Hey, can you get my staff smart? Can you get my unit smart? So I've done that. I've done a lot of Marine Corps and Navy, as well as some of the Joint Force, combatant command and stuff. So just email me or find some time on the schedule. I'm happy to come in and do it if my schedule permits. It's designed to get people smart on that. It's not an academic. A lot of the academic 101 courses are an introduction to something, but an introduction designed to be the foundation for you to go on and get a degree in that field. Right? Knuckle Draggers is not. It's not. This is the first step of your PhD in artificial intelligence. So a lot of times 101 courses introduce concepts in depth that you don't need to know unless you're going to go to that field. We stripped all that out and said, look, this is for you to understand it. This is a one and done. If you've got curiosity, there's a lot of paths you can go pursue. There's books you can read, things you can go look online. But the best way you just reach out to me and we'll set that up.
Sir, so I'm going to turn it over to you for some closing comments if you have any, and then that'll be the finish this up.
Nope, I appreciate that. You can obviously tell I'm kind of passionate about AI. It's an interesting technology. One of the senior leaders at one of our technology partners, the $1 trillion company, he said to me, hey, Jack, I've been doing this for 40 years, working in technology, and I've never seen an organization as far behind on any particular technology as the DoD is on AI right now. And I don't have his experience on looking at all the different companies, but I tend to agree. It's a technique and a tool that we can use to do a lot of things. And it's applicable to the range of missions across the DoD mission set, right? From warfighting, corporate functions, it can help us recruit, it can help us with medicine, it can help us do a lot of things. And so it can't do everything. It's not magic pixie dust you can just put on it, but I do think that we're leaving a lot on the table from inefficiency and inability to accomplish the mission by not employing it better. And we are, by definition, an organization that needs to compete with adversaries, thinking adversaries that think very hard about how to beat us, right? And if we are not bringing the best of the technology that exists to that fight, we are likely opening ourselves up to a gap that, because for whatever reason we don't want to use the technology or don't think it's something, then an adversary that learns they can use it against us could beat us, right? And in war, technological gaps typically get closed quickly, but over 3 to 6 months. And we had some interesting gaps over Japan and Germany in World War II. Radar for gunnery at night, proximity fuses made anti-aircraft fire way more valuable, right? And so those were never countered. So we were able to maintain that. But you saw in Russia, they were able to counter early Ukrainian innovation with their adaptation. We will eventually adapt if somebody comes at us and finds ways to use technologies against us we weren't expecting. But it could happen inside a window of time in which something happens that we then decide not to reverse. It'll put us in a position where it's a lot harder to go reverse it than potentially prevent it in the first place. So when I look at AI, I see that we are not, it's a technology with a lot of potential we are not employing for the jobs we need to do. And that is putting us at risk. It's leading to retention issues. It's leading to a lot of things, cost overruns, because we are continually diverging from the way the private sector is using technology. And that's putting us at a cost disadvantage and a recruiting disadvantage because people want to come work for an organization with crappy technology. So to me, I feel we have to get better at this. And I say to people, it's like, look, I believe in AI. I'm a skeptic of AI. I don't think it'll do everything. It's like people are like, it's magic elixir. It's like, no, it's not. It's going to kill the world. No, it's not. I'm not scared of AI. I don't think it's going to do everything. But that really then puts the onus back on us to go, okay, if you have this tool, what is it used for? It's very useful for certain things and completely useless for other things. You got to identify the things it's useful for and make the investment to go after that, while not being pulled away by that shiny object of like, oh, I want to kill a robot. You're like, sorry, that's not how this stuff works. So that would be my final thoughts. Get smart on this to understand it. The other technologies throughout history, people have gotten smart on. The younger generation is now getting smart coming out of school, but we've got this gap where our middle to senior management didn't grow up with this technology, didn't know what it was, and it evolved very rapidly underneath their noses, and that's why we're trying to rapidly upskill them.
Sir, thanks for your time and your insight and
Absolutely.
driving down to be with us today. Thank you to those folks who are going to join us in the future on Spotify and YouTube. That's all we have for this episode, so go ahead and carry out the plan of the day.
Thank you.
Thanks for joining us. As always, we depend on support and feedback from the Team Krulak community to constantly improve our offerings and reach a wider audience. So if you have feedback on this episode, please take a moment to fill out the survey linked in the show notes to help us do better. Also, if you have enjoyed this episode, please hit the like button and subscribe to our channel on YouTube or leave us a review on the podcast app of your choice. It truly does help us reach a wider audience. Thank you as always for your support, and we'll see you on the next episode.
Education is what's important. Training, preparation for the expected. Education, preparation for the unexpected.